Welcome to the Explainer. You ready to really level up your coding game? Today, we're unlocking the 4 foundational principles of object-oriented programming. And if you're a BTech student wrestling with Java, trust me, this is the stuff you absolutely need to know.
So here's our game plan. First, we're going to tackle why we even need OOP in the first place. Then, we'll break down each of the 4 pillars, one by one. And finally, we'll see how they all lock together to let you build some seriously powerful software.
All right, so before we dive into the nuts and bolts, the how of OOP, let's take a step back and talk about the why. Why did we even invent this stuff?
I mean, have you ever been there? You're deep into a big project for one of your courses, and the code just becomes this tangled mess. It's a total nightmare to fix anything or add a new feature without breaking something else.
And this is the problem OOP was born to solve. It's way more than just a set of coding rules. It's a complete shift in how you think. It's all about modeling your code around real-world things, or objects, which just makes everything click. It becomes so much more intuitive and way easier to manage.
Okay, let's grab the first tool from our OOP toolkit. This is Encapsulation. And the best way to think about it is as a protective shield for your data.
You know, it's kind of like a medicine capsule, right? The plastic shell protects the medicine inside from everything else. In your code, encapsulation does the same thing. It bundles an object's data and the methods that work on that data together, keeping it safe from being changed by accident from somewhere else in your program.
So how do you actually do this? Well, it's a pretty simple but brilliant 2-step process. First, you declare your variables as private. That basically locks them down. Then, you create very specific public doorways. We call them setters and getters, that act as the only controlled ways to read or change that data.
But here's a classic problem you'll run into. What happens if a parameter in your method has the exact same name as one of your class variables? That's where the this keyword becomes your best friend. It's a special pointer that says, hey, I'm not talking about that temporary parameter. I'm talking about the variable that belongs to this specific object. It just clears up all the confusion.
All right, pillar number 2, inheritance. This one is a huge deal, and it's all about not reinventing the wheel. It's about code reuse.
It's literally like a family tree. A child inherits traits from their parents, right? Same thing in OOP. A subclass, the child, can inherit all the fields and methods from a superclass, the parent. This is amazing because it means you can write common code once in a parent class and then reuse it in all of its children. And in Java, you've got a few different flavors of this. You've got your straightforward, single inheritance, a simple parent-child link. Then there's multi-level, which is like a grandparent-parent-child chain. And you also have hierarchical, where one parent class can have multiple different children branching off from it.
So that begs the question, right? How does the child class talk back to its parent? What if it needs to use one of the parent's methods or its constructor? Well, it uses another special keyword, super. This is super useful, no pun intended, when you want to add to what the parent does instead of just completely replacing it.
Okay, moving on to our third pillar, and this one's a bit of a mind-bender at first, but it's incredibly powerful. It's called polymorphism, which literally just means many forms.
But the concept itself, it's actually super simple. Think about it like this. You can tell a bunch of different animals to speak. The action is the same, speak, but the result is totally different, right? A cat meows, a dog barks. One action, many different outcomes. That's polymorphism.
So, in the world of code, this means we can have a single method name, like calculate area, that can do different things depending on whether it's called for a circle or a square. It makes your code incredibly flexible.
Now, this is where it gets really interesting, because polymorphism isn't just one thing. In Java, it comes in 2 main flavors. First, you have method overloading, which is decided when you compile your code. Java looks at the method name and its parameters to figure out which one to run. Then you have method overriding. This is the really dynamic one. It happens when your code is actually running, and the specific method that gets called depends on the actual type of the object.
And what's the secret sauce that makes all that runtime magic with method overriding possible? It's something called typecasting. This is a huge concept. It lets you treat a very specific object, like a Maruti object, more generally as a car object. This is a game changer because it allows you to write code that works with any kind of car without having to know the exact brand beforehand.
And that brings us to our fourth and final pillar, abstraction. Now, if encapsulation was about hiding your data, abstraction is all about hiding the complexity. The classic example is making a phone call. Think about it. You pick up your phone, you dial a number, you talk. That's it. You don't need to know anything about how the signal travels, how it connects through cell towers. All that internal processing is completely hidden from you. You just get the simple interface.
And that's the whole point in programming. Abstraction lets us focus on what an object does, not how it does it. We get to interact with a simple set of controls while all the complicated, messy details are tucked away out of sight.
So how do we pull this off in Java? Well, you've got two main tools in your belt. First, you have abstract classes. You can think of these as partial blueprints. They can provide some of the implementation, but leave other parts for the child classes to figure out. Then you have interfaces, which are pure blueprints. An interface just lays down the rules. It says any class that implements me must have these methods, but it gives zero details on how to actually build them.
Okay, we've covered a lot of ground. So let's take a second and see how all four of these pillars, these big ideas, actually work together as a team to help you write way better software. Let's just boil it all down. Encapsulation? That's your data shield. It protects your object state. Inheritance? That's your efficiency expert. It lets you reuse code. Polymorphism? That's what gives your code flexibility and makes it dynamic. And abstraction? That's your complexity manager. It keeps things simple. Put them all together, and you have a powerful way to build software that's strong, easy to change, and ready to grow.
So look, now you have the blueprint. By really getting a handle on these four principles, you're not just learning the syntax of a language, you're learning how to think like a software architect. You have the tools to build entire worlds with code. The only question is, what are you going to build first?